Okay, today we're going to talk about the intermediate value theorem. It's basically a theorem that tells you that a value exists between two other values. It doesn't give you the exact value. It just, again, is almost like a proof theorem in the sense that it tells you an existence theorem, if we want to call it that. Basically what it is if you, and here's the key, a function that is continuous. You have to have a function that is continuous in order for you to be able to state that this is true. If we know that there's a y value between two y values, f of a and f of b, it means that the c value that y value happens at in the x has to be between the x's of a and b. Alright, and let's look at this in theory. Basically, it's saying to get from point A to point B, you're going to have to cross through, to get from this value to this value, between here and here. And then if the line is continuous, means there's no break, there has to be a spot in between A and B where it crosses this y value, or else there's no way to get to the other point. It just doesn't happen. Again, has to be continuous. So let's see how we can use this in practice. Is any real number exactly 1 less than its cube? Okay, well, let's call the real number x. Is x equal to 1 less than its cube? Its cube means you're taking that number and cubing it and then taking away 1. So here we have our equation. Now whenever you have a polynomial equation like this that's bigger than just a linear equation, the best way to solve it is to get it equal. Well, the way to solve it is to get it equal to 0 and look for the zeros of the function. So when we set this equal to 0, we get x cubed minus x minus 1 is equal to 0. So I want to know, is there any real number exactly 1 less than its cube? Well, using the calculator you could easily just figure this out. But we're looking for the 0. So we're looking for, and what happens when y equals 0? You're looking for when the function changes signs, pretty much. So what we're going to do is look at the calculator real fast and get some table of values. I'm going to find out when the function is at -1, -2. I'll just start at -2 actually. And you don't have to do all of these. I'm just showing you what we're looking for here. Okay? So, by the way, the first thing that's important here is this is continuous because it's a polynomial, and all polynomials are continuous. This function, I should say, is you don't include the 0 really, but this function right here is continuous. So when we graph this, it'll be continuous. So that's part 1. Part 2, and you can do this by hand or with the calculator. I'm going to just look at the calculator real quick and look at my table of values. When x is equal to -2, we have -7, -1, -1, -1, and then 5. So what that means is that I have -7, -1, -1, -1, and 5. Well, I want to know when it equals 0. Between which two x values will you find your answer? Well, based on just looking at my table of values, we go from a negative value to a positive value. So it changes signs here. So we would say, since it's continuous, there must be a point between x equals 1 and x equals 2 where the functions equal 0, where f of x is equal to 0, which is what we want it to be because that's what we're solving for. So again, the key is you need to state that since it's continuous, because if it's not continuous, then it might jump past that and there might not be a value. That's why it's key. And that's really all you have to do, is say that's continuous, give me some values, and show that sure enough between this one and this one, this x value and this x value, it goes from -1 to 5. And then to actually solve it, solve using the calculator. All you do is go to your y1, y2, second trace 5, enter, 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 and it should jump over to where that point is. And sure enough, when it goes through the 0, x is 1.325. So we would say that the value It happens when x is 1.325. Again, the theorem itself did not tell me that value. The theorem just told me which two values it's between. The theorem told me that it has to be between 1 and 2. Okay? So that is how you would use the intermediate value theorem. This is basically it right here. And the table. Okay? Alright, now, we're also going to sketch some graphs. I don't have a limit at 3, but the limit from the left is -2. The limit from the right is 3, and so is the value of the function. So I'm going to just say that I have, when x is 3, that's where everything's happening. And then I have a value of 3 in the y and a value of -2 in the y. So when I'm at -2, that means the limit as approaching from the left is -2, but the function does not equal it. So I'm going to put an open circle here. The function equals 3 when you're at 3, so there's a dot here. And the limit from the right is 3. So basically what that's saying is, I can put anything I want over there. As you're coming from the right, you approach 3 in the y, which you do. And I can just draw that way. If you're coming from the left, you're approaching -2. And that's it. Again, these lines could look like something else. Just make sure that they keep a function. And that's all you really need. Just some sketch that shows me you understand what I'm asking for. This one, it's continuous for all x except when x is equal to +2. So I'll put a 2 there. And it has a removable discontinuity, which means it has a hole at 2. But it's continuous everywhere else, so you can pretty much just draw lines shooting off from both sides. It's continuous except for there. And removable means there's a hole. This is the tricky one. Because we've been working with limits for the last couple sections, we've been working towards, moving away from the point or towards the point. But with the words increasing and decreasing, that means from left to right. So I'll write that as a side note here. Look at increase or decrease for the function from left to right. Don't work from the middle point and move left and then move right. So what that means is, I'm going to just make some random thing here. We're at 3, it looks like. 1, 2, 3. There's no limit at 3, which means it's going to be a jump discontinuity because it's split. And we have, so I'll put a point here, just whatever here, and then a point here. And so when it's to the right of x equals 3, it's decreasing. So that means that I need it to go down from this point. So you can just draw that. If we're left of 3, the function's increasing. This is where you have to be careful. This is what's wrong. People will say, oh, I'm at this point, I want it to go up. But if you go that way up, the function's actually decreasing as you move from left to right. So what you want to do is say, okay, I'm way down here. It needs to be increasing towards that point, and that is now increased. So that's where people can get a point off sometimes. Increase and then decrease. Remember, you're working from left to right with that. Okay? And that would work for this graph. Finally, find the value or values of a such that the function, or so that the function is continuous. Well, again, in order to a piecewise to be continuous, the two limits, so from the left and from the right, have to equal each other. It's almost, think of it as there's a discontinuity, a jump discontinuity. We've got to line the graphs up. So we need to figure out what value will line these graphs up at x equals -1. So to do that, if it's continuous, then the left and right need to equal -1. I should say they need to equal each other at -1. When x is equal to -1. So if we look at the left-hand limit, that means all the values from the left, which is this one, but we're going to figure out what the value is at -1 there, so it's 4 minus -1 squared. And we want this to equal a times negative 1 squared minus 1. So we're going to solve this. We get 4 minus, this becomes just a 1. This becomes a 1, or a minus 1. So this is 3 plus 1 is 4. A equals 4. So, in order for it to be continuous, a needs to be, sorry about that, a needs to be 4. Okay, so, and that's all we have.